All right, we are going to continue on in chapter 5, and we are going to be moving into section 5.5, which is titled Complex Eigenvalues. So in this section, we're going to kind of repeat the process that we did in the 5.1 and 5.2 video a couple of videos ago, except now we're going to move into the idea of the complex world when eigenvalues and eigenvectors involve those types of numbers. Now, some of y'all may not be as familiar with complex numbers as others. So what I would like to do is we're going to do a kind of a quick little mini overview of what complex numbers are and where they come from and what you're going to be getting in this section. So the first part is kind of the linear algebra part, and then I'll kind of do the basic algebra stuff. The matrix eigenvalue eigenvector theory that we've already developed for the nth dimension of the real space. So that was section 5.1 and 5.2. Is going to now apply equally to what we call the nth dimension of the complex world, which pretty much means that we are going to have complex numbers in our eigenvalues and in our eigenvectors. The good news is for y'all that you don't do the work any differently. It's just the answer you're going to get is going to look a little bit different. What I mean by that is you're still going to find your scalar lambda by taking the determinant of a minus lambda I and setting that equal to 0. The difference will be it'll be a complex number. And then there will also be a non-zero vector x in the nth dimension of the complex space that satisfies that popular equation that kicked off this whole chapter of a times x equals lambda times x, where a is a matrix and lambda is a scalar. If you do have complex numbers involved with these answers, it's fine. You can simply call these still eigenvalues and eigenvectors, but more specifically, as we learn this today, I will usually use the verbiage complex eigenvalue and complex eigenvector. Now, the question probably is for a few of y'all is, well, okay, what's a refresher or what are complex numbers? I don't quite remember those. Well, one thing before we get to a complex number is the big thing. This involves imaginary numbers. So if you've never worked with imaginary numbers before, we don't do a whole lot of them in this class, but there is one basic thing you need to know, that we define the imaginary number I as equaling the square root of -1. And this was developed a long time ago as a way to solve the quadratic equation x squared plus 1 equals 0. Because if you try to solve that directly, you're going to end up with the square root of -1, which is thus going to be I going forward. Now, root -1 is not the only term there. It can be the root of any negative number. So a couple examples of that. If we run into a problem today where it says take the square root of -9, we know the square root of 9 is 3, but since it's negative, we have to attach the imaginary number to that. So that would be 3i. Likewise, if you get a problem that doesn't become a perfect square root, so let's say something like the square root of -20. So I know that 20 breaks down into 4 times 5, and I know that root 4 is 2. So when we normally break this down, we would bring a 2 out to the front, and we would leave the 5 on the inside. But since it is negative, that means you have to also bring out the imaginary number, and so the square root of -20 will become 2i times root 5 if that's our problem. So that's where imaginary numbers show up. As far as the idea of complex numbers, well, first of all, a definition. Complex numbers are written in the form, get my highlighter back out, a plus or minus b times I. So you're going to have two parts to every complex number. You have the a portion, which is what we call the real part of a complex number, and then you have the b times I, which is called the imaginary part of a complex number. Now, these two parts can either be added or subtracted depending on the problem that you're doing, but both of those put together is what we call a complex number. The I is just the imaginary part of a complex number. All right, so other than that, we're going to work 4 problems here that are very similar to what we've learned. There is one small change we're going to see in a little bit, but the first 2 are pretty much what we did in the first video of chapter 5. What I would like you to do is, given this 2x2 matrix, I want you to find the eigenvalues and a basis for the eigenspace for each lambda working in the second dimension of the complex space. So remember from the last couple of videos that when you want to find eigenvalues, that we will do here in red, imagine that you are subtracting lambda from the main diagonal, all right? Because remember, your job is to find what is the determinant of A minus lambda I. So I'm going to find the determinant of this 2 by 2 matrix. That would be 1 minus lambda times 3 minus lambda minus, and then negative 2 times 5 is negative 10. And we will eventually set this equal to 0. All right. So multiplying some stuff out, if we FOIL those two polynomials together, you should get 3 minus lambda minus 3 lambda plus lambda squared plus 10 is 0. And then if I combine like terms and put stuff in standard form, you'll get lambda squared minus 4 lambda plus 13 equals 0. Now you can try all you'd like. You're not going to be able to factor this problem because there's not two numbers that multiply to get 13 and add to get negative 4. So hopefully you remember from algebra back in the day, that to solve a quadratic that doesn't factor, you have to do the quadratic formula. So as a refresher for your notes, the quadratic formula is typically found by doing negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is your coefficient of the quadratic, b is your coefficient of the singular term, linear term, and c is your constant. Plugging those three numbers into my quadratic formula, I can find lambda to equal negative of a negative 4 plus or minus the square root of negative 4 squared minus 4 times 1, which is a, times c, which is 13, all over 2 times a, which is 1. So simplifying this, you should get positive 4 plus or minus, and then this middle part, the inside of the radical part, you are more than welcome to type that in your calculator. Looks like you're going to get 16 minus 52. And so 16 minus 52 is negative 36 divided by 2. So that will give you 4 plus or minus, and as we talked about a few minutes ago, the square root of negative 36 would be 6i, all divided by 2. And so if you divide the 2 into the two terms in the numerator, you get eigenvalues of 2 plus or minus 3i. And so you've just answered the first half of your question. Just like back in 5.1 and 5.2, when you have a 2 by 2 matrix, generally you pick up at least 2 eigenvalues. Well, that doesn't have to be necessarily true. That's typically what's going to happen today. All right. From here, you now have to find the basis of each eigenspace, and you've got to do one for each lambda here. So beginning with our first one, and it doesn't matter which one we do first because we got to do them both. Let's do 2 plus 3i. So remember, when you set up a basis of an eigenspace, you go back to the original matrix that has the minus lambdas on it, and you're going to substitute the lambda into that and simplify. Now keep in mind, since for example in the top left corner, you're going to do 1 minus 2 plus 3i, don't forget that you are distributing the negative to both terms, so you actually get negative 1 minus 3i. The 5 and the negative 2 don't change. And then if you do the same thing, if you do 3 minus 2 plus 3i, you're going to get 1 minus 3i. And then we have to make this an augmented matrix as the homogeneous form, so we're going to add the 0 vector column on the end. Now the difference of row reducing a complex, or I guess a matrix with complex numbers in it, is that you can't do it. This is the best you're going to get. But we still need to be able to create some information about our eigenspace. So my general rule that I tell students here is that looking at the two rows you're given, you don't need to use both of them, just use one or the other. I typically pick the one with the smaller numbers. So I'm going to pick row 2 to focus on here. Row 2 tells me the following. It says that negative 2x1 plus 1 minus 3i times x2 must be 0. Now from there, I highly encourage you to solve for the variable that doesn't have the complex number attached to it. So for us, that would be x1. If I wanted to get x1 by itself, I'd actually move the negative 2x1 over. So you would have 1 minus 3i times x sub 2 equals positive 2x sub 1. And then if you divide both sides by 2, we see that 1 minus 3i divided by 2 times x sub 2 will be your x sub 1. Now, this is the equation that generates the infinitely many eigenvectors in your eigenspace. So we're done there. But you just want a basis, so you just need one vector that makes this true. So as far as calling this v sub 1, creating my vector here, notice that in the way that we wrote this, since x2 is the variable next to the expression, this is our free variable, while x1 is our basic variable. So you are allowed to let x2 be any number that you want it to be. Now, since it's being multiplied by a fraction that has a 2 on the bottom, I'm actually going to suggest that we let x2 be 2 in this case. All right. I do that because if I let x2 be 2 and I multiply it by the ratio cancels, or the fraction cancels, and just gives you 1 minus 3i. And I forgot my squiggle braces. That would be the basis of the eigenspace for lambda equals 2 plus 3i. Now, as we've learned in the last two videos in chapter 5, once you do one, you still have to do the other one. So let's move to our second eigenvalue, which is lambda equals 2 minus 3i, and let's create our new augmented matrix. Plugging this lambda into your matrix A with the minus lambda I, if you do 1 minus this new lambda, you should get negative 1 plus 3i, 5, negative 2. And then if you do 3 minus this new eigenvalue, you should get 1 plus 3i with a 0 column on the end. Once again, you can pick either row you want to, but what I'm about to show you here in about 2 minutes in this problem is that a nice little shortcut we're about to develop. But in order for us to see this shortcut, here's what we have to do. Since I picked row 2 the first time I did this, let's be consistent and keep the same row and watch what happens here. You're going to end up with negative 2x sub 1 plus 1 plus 3i times x sub 2 needs to equal 0. Solving for x1 again, you should get 1 plus 3i times x sub 2 is equal to positive 2x sub 1, and thus 1 plus 3i all divided by 2 times x sub 2 should be x sub 1. Once again, you'll notice that x2 is your free variable and x1 is your basic variable. So when I create my second basis of an eigenspace, you're only going to have one vector because you only have one free variable. Let x2 be any number you want it to be. My advice, pick the same number you picked beginning with. We picked 2 on the first one, let's pick 2 again. And then if you plug x sub 2 equals 2 in, you will just get 1 plus 3i. And that is the basis of the eigenspace for your second lambda. Now, what you'll notice, and what I hope you notice here, is that going forward, we will not have to find both bases in these problems. We'll just be able to find one, and we can automatically know what the other one is based on the properties of complex numbers. You'll notice that these two bases over here on the right, if I can get my, there we go, get my pen to work. The only difference in these two bases was that the complex number portion of your eigenvector changed signs in the middle. It went from 1 minus 3i to being 1 plus 3i. Now, if we do a problem in a minute where the first one is a plus, the next one I know is going to be a minus. The free variable that you pick on the first one Let it be the exact same free variable so this can work, and ta-da, you will always get your second eigenvector immediately. So going forward, if I ever want you to find all this information, which we're about to do this again on the next slide, you need to find your lambdas, pick one of your lambdas to find the basis of the eigenspace, and then by default, you will pick up the other one as well. All right, so let's look at a second example to see if we can kind of talk through this shortcut here. Once again, you are given a 2 by 2 matrix, and the instructions are saying to find the eigenvalues and a basis for each eigenspace in the second dimension of the complex field. So going through the same steps again, I want to imagine that there is a minus lambda down the main diagonal, because you are about to find the determinant of a minus lambda I, and you're going to set that equal to 0. So when I find the determinant of this 2 by 2 matrix, you get 4 minus lambda times 4 minus lambda minus a negative 9 is equal to 0. Multiplying or foiling your first two polynomials, you should get 16 minus 4 lambda minus 4 lambda plus lambda squared plus 9 is 0. And then you will get lambda squared minus 8 lambda plus 25 is equal to 0. Once again, this does not factor. So over here to the right, we're going to do the quadratic formula again, with A being 1, B being negative 8, and C being 25. So you can use the same formula from the last slide. I'm not going to write it down again because we've already got it there in our notes, hopefully. But to find lambda here, we're going to take negative b, so negative of negative 8, plus or minus the square root of b squared minus 4 times a times c, all of that divided by 2 times a. Simplifying this, you should get positive 8 plus or minus the square root. So inside the radical, you're going to get 64 minus 100, which just coincidence here is also negative 36 times 2. This becomes 8 plus or minus 6i divided by 2, and then dividing each of the top numbers by 2, you get your two eigenvalues. Lambda has to equal 4 plus and minus 3i. Now that we have both of our eigenvalues, we now know the trick to find both eigenvectors. But once again, you still got to find one of them before you can use this shortcut. So pick whichever lambda you want, and you can try whichever one you like on your own if you want to. I typically go with the plus one until I have to change my mind, which I am going to show you in a minute. There's going to be a time you have to, so we will do that, but we'll do plus for right now. I'm going to create my augmented matrix. So remember, you're going to plug the 4 plus 3i into your original A minus lambda I matrix. So if I do 4 minus this lambda, you should get negative 3i after distributing the negative. Then you're going to get 3, negative 3, and then you're going to get the same thing in the bottom, which is negative 3i. Throwing the 0 on the end, there you go, for the vector. Now, these do reduce if you'd like to go ahead and do that, but it's not really necessary because you're going to reduce on the next step either way. Pick whichever row you think is easiest. Now, in one like this, it really doesn't matter. You can go either route, and it's just as simple as the other one. Just to be different from the last one we did, I'm going to use row 1 this time, just to be different. If you always want to use row 2, you can. But row 1 tells me that negative 3i times x sub 1 plus 3 times x sub 2 must be 0. And remember, you solve for the variable that doesn't have the complex number on it. All right, so we're going to solve for x2 here. If I move the x1 term over to the right side, you will get that 3 times x sub 2 is positive 3i times x sub 1. And if you divide both sides by 3 here, you should get the expression that x sub 2 is equal to I times x sub 1. In this case, x sub 1 is your free variable, and x sub 2 is your basic variable. So when we go to write the basis of our eigenspace, so we'll just call this first one v sub 1. There's only one free variable, so we're only going to have one vector here. We can let x sub 1 be any number we want to. And I don't see a fraction here, so I'm going to make it really easy. I'm going to let x sub 1 be 1 because there's no fractions I need to cancel. If I let x sub 1 equal 1, then x sub 2 is just going to become I. And so this is the basis for 4 plus 3i's eigenvector, or eigenspace, I should say. Now that you've done the work, I don't need to see any work for the next one. When I ask for lambda equals 4 minus 3i, we should be able to immediately jump to the one vector that will make up the basis of the eigenspace for our second eigenvalue. Remember what I told you. Whatever the free variable is, keep that the same. So that would be 1. Now the problem here is that if you're looking at just I, it doesn't look like the one we did before. But remember from earlier, I is the same thing as 0 plus I, because every complex number has a real part, and if you don't see it, it's understood to be 0. When we do this shortcut, our rule says we have to change the sign that's in between the real and imaginary part. So instead of 0 plus I, R should turn into 0 minus I, and we should all know that 0 minus I is negative I. And ta-da, you're done. That is the basis of the eigenspace for your second eigenvalue in this problem. And we typically only do 2x2s in this section because the larger this gets, it gets a lot more complicated, and we're not going to see a whole lot of complex numbers in chapter 6, but we will see them occasionally, so I want you to be prepared to deal with those. All right, so now that we know how to find the eigenvalues and basis of eigenspace using the complex world, let's move into the one application for right now that we can talk about. So for this theorem, we're only going to work with 2x2 matrices because in the 3x3 and higher dimensions, this theorem doesn't work out as nice, so we're not going to trouble ourselves because we would have computers do that for us anyways. But to be able to see you do this by hand, I think a 2x2 is reasonable. So let's let the matrix A be a real 2x2 matrix with a complex eigenvalue of lambda equals A minus BI and an associated eigenvector V in the second dimensional complex field. Now, what this all means, before I get into the formulas here, is that every element of the original matrix will be a real number. So there won't be any i's in the original matrix, just like we saw. We just learned that when you find the eigenvalues in a complex field, you're usually going to get 2. You're usually going to get the A value plus and minus the BI value. For this theorem, and the way I'm going to define the formulas here, we only need to use one of the lambdas. The only lambda you will need is the one that has the subtraction in it. You can find the plus one. It doesn't really help us with anything, but we're going to use the minus for this problem. Using the minus one, you need to find the eigenvector based on that particular lambda, or once again, this theorem will not work. What this allows us to do is it allows us, if you remember back from diagonalization in the last video, when we did PD, P inverse, the problem is that complex eigenvalues don't generate diagonal matrices. Instead, we do this slightly different but similar formula. We're going to break down A into the factorization of P times C times the inverse of P, where we're going to define the matrix P. All right, using the eigenvector V you find in this theorem, the real elements of the eigenvector will make up the first column. So you'll pull off the real parts, and I'll show you how to do that in a minute. And then you'll pull off the imaginary parts of the eigenvector, and that will make up your second column. Then you can find your C matrix by taking the A and the B value that you find in your lambda. So this A and this B, whatever those two numbers are, not looking at the negative there, this is how you create your C matrix. You take the A element and you put that in both locations on the main diagonal. Whatever the B value is, you put the negative of that in the upper right and you put the positive of that in the lower left. And that will always be the middle matrix of this factorization. And then obviously once you find P, since it'll be a 2 by 2 matrix as well, we can use an algorithm to find its inverse, which we'll review here in just a few minutes. So this is our last little thing for this video. We're going to kind of repeat the process again for the last two problems, but we're going to add a step where we keep going into the factorization. So let's do the first of two here. I would like you to diagonalize the matrix if possible, which is pretty much the same thing as saying factor the matrix if you can. All right. I made up the matrix 3, -3, 1, 1. So we need to find lambda before we can do anything else. So just like the first two problems, I'm going to subtract lambda. Sorry about that. I accidentally closed the app. All right. So we are going to subtract lambda from the main diagonal. We're going to find the determinant of a minus lambda I and set that equal to 0. So that will become 3 minus lambda times 1 minus lambda minus 3 times, -3 times 1 is -3, and set that equal to 0. Working this out, you should get 3 minus 3 lambda minus lambda plus lambda squared plus 3 is 0, which becomes lambda squared minus 4 lambda plus 6 is 0. Let's do the quadratic formula again. We're going to let A be 1, B is going to be -4, and C is going to be 6. So lambda will come out to be negative B, or negative of a -4, plus or minus the square root of -4 squared minus 4 times A times C, all of that over 2A. Simplifying this out, you should get +4 plus or minus the square root. Inside the radical, that's going to be 16 minus 24, which is a -8, divided by 2. I can break down the square root of -8. So let's see. I know that 8 is 4 times 2. So with the negative as well, this should break down into 2I root 2 over 2. And then if I divide the 2 into both terms, you will get 2 plus or minus I times root 2. Now, even though we found both eigenvalues, because it's kind of just part of the formula, for this problem, the only lambda that you need to be using is the one with the minus for that theorem to work. Using that particular lambda, use that to find the basis of your eigenspace. So down here, for that one, we're going to do lambda equals 2 minus I root 2. Developing this augmented matrix, if you plug the lambda value in, so if I do 3 minus that, you should get 1 plus I root 2, -3, 1. And then if you do 1 minus this lambda, you'll get -1 plus I root 2, with a 0 vector added on the end to make it a homogeneous equation. Pick whichever row you want to. It looks like I'm definitely going to pick row 2 here because it has lots smaller numbers in it. And that should tell us that x sub 1 plus -1 plus I root 2 x sub 2 should equal 0. I'm going to move this entire term over to the other side because you're trying to get the x sub 1 by itself here. So x sub 1 is going to equal the negative of -1 plus I root 2 x sub 2. Because since that term's being added to the x sub 1, you have to subtract the entire thing over to get it to the other side. All right. So we're going to develop our vector here. So pick your free variable. So in this case, our free variable is x sub 2. Honestly, what I'm going to do here is I'm actually going to let my free variable be -1, because if I let x sub 2 be -1, it will cancel that negative that's in the front of my parentheses and just leave me with an x sub 1 value of -1 plus I root 2. Now that we have the basis of our eigenspace of the A minus BI eigenvalue, we can now start to do our factorization. So down here in blue, we can first find our P matrix. So remember, our P matrix says you're going to use your eigenvector and you're going to pull the real and the imaginary parts off individually. The first column comes from the real values of your eigenvector. Now, if you look in the first and the second entry, both entries have the same real value, which is -1. So I'm going to put a -1 in both entries of the first column. In the second part, the imaginary part, the first element has a root 2 attached to the I, and there is no I term in the second part. So that means my second column is going to have a root 2. So you don't want the I part. Remember, you just want to use real values. So we just use the root 2. And since there is no I in the second element, it's understood to be 0. We can also find our C matrix. So recall that our C matrix says you need to identify your A and B value. In this case, your A is the real part of your eigenvalue, and your B is the number attached to I, which is root 2. Whatever the A value is, so A is 2 here, that number has to go on both entries of the main diagonal. And then the root 2, which is the imaginary part of your lambda, the negative of that goes in the upper right-hand corner, and the positive of that goes in the lower left. So you pick up a C matrix of 2, -root 2, root 2, 2. And then finally, you want to find your P inverse matrix. So P inverse, just take the inverse of P by using our algorithm from chapter 2. That would be 1 over the determinant of P. So if you find the determinant of P, that would be 0 minus a -root 2, which is just root 2. For the algorithm, you flip-flop the main diagonal. So we'll put a 0 up top and a -1 at the bottom right. And then the two numbers on the other diagonal, you negate those. So you'll get a +1 in the bottom left and a -root 2 in the top right. And then you need to distribute that constant that you just got through. So we should end up getting a 2x2 matrix of P inverse as 0, -1, 1 over root 2, -1 over root 2. And now you have your 3 parts of the factorization of this 2x2 matrix. So I'm not going to put them all together because the homework's not going to make you do that either. But remember, you have just broken A down into the form P times C times P inverse, where the P and the C matrix help you illustrate the eigenvalue and eigenvector of your matrix. All right. Let's do one more so you have a second one for your notes, and this is how we're going to wrap up this video for section 5.5. I would like you to diagonalize, aka factor, the following 2x2 matrix. So for the 4th time in this video, we need to find the eigenvalues. Once again, imagine you have a minus lambda down the main diagonal, and let's set up the determinant of A minus lambda I and set that equal to 0. So the determinant is going to end up being 5 minus lambda times 3 minus lambda minus a -2 is equal to 0. This becomes 15 minus 5 lambda minus 3 lambda plus lambda squared plus 2 is 0. And then this can be rewritten as lambda squared minus 8 lambda plus 17 is 0. So for our quadratic formula this time, A is 1, B is -8, and C is going to be 17. So when we do our quadratic formula, lambda will be the negative of -8 plus or minus the square root of -8 squared minus 4 times A times C all over 2 times A. So this ends up becoming 8 plus or minus the square root. Let's see, that is 64 minus 68. So that would be -4 divided by 2. This becomes 8 plus or minus 2i divided by 2. And so divide the 2 into both of those numbers, and you get 4 plus or minus I as your 2 eigenvalues. Now, for the factorization of this, we don't need both of them. We are just going to focus on the one with the minus sign. Using that particular lambda, you now want to find a basis of its eigenspace. So for lambda equals 4 minus I, let's create our augmented matrix. Plug the 4 minus I into the matrix with the minus lambdas. And so let's see, 5 minus our lambda would be 1 plus I, -2, 1. And then 3 minus our lambda is going to be -1 plus I with a 0 vector on the end. Once again, it doesn't matter which row you technically pick. I always pick the one with the smaller constant. So I'm going to pick row 2 again, which tells me that x sub 1 is going to, not equal, x sub 1 plus a -1 plus I times x sub 2 should equal 0. And so if I solve for my x sub 1 here, so I'm going to subtract this entire term over, you should get the negative of -1 plus I x sub 2. So remember, x sub 2 is your free variable here. So when I create my eigenvector that I'm going to use in my factorization, I'm going to let x2 be any number you want it to be. Just to be different on this one so you can see different ways so you're not seeing the same process over and over. In the last problem, I let x sub 2 be -1 to cancel the negative. Let's assume this time I just want x sub 2 to be 1. So if I'm going to let x sub 2 just be the number 1, this negative in the front is not going to cancel. So thus you have to distribute it to both terms, which will make the first element 1 minus I in your eigenvector. All right. Now that you have your eigenvector and we also have our lambda from earlier, we can start to do our factorization elements. So beginning with P. Matrix P is going to be the 2 by 2 matrix where the first column comes from the real values of your eigenvector. So in this case, both parts of the eigenvector have a real portion of the number 1. So we're going to put a 1 in both spots down the left column. The second column comes from the constants of the imaginary part, which in front of this I is a -1. And since there is no I in the second part, it's understood to be 0. Your C matrix comes from your eigenvalue that you're using, where in this case, A is going to be the 4, and then technically B is going to be 1 in this case, because we don't include the negative as part of this. So whatever your A value is, which is 4, that's the elements on the main diagonal. And then the 1, which is your B value, the negative of that goes in the upper right corner, and the positive of that goes in the lower left corner. Your last thing to do is to find P inverse. So we can use the same algorithm as the last problem, where we're going to take 1 divided by, find the determinant of P. So that would be, determinant of P down here would be 0 minus a -1, which is just going to be +1. As far as the elements of P in this formula, you flip-flop the main diagonal. So flip-flop the 0 and the 1. And then you negate the other diagonal. So you'll have a -1 in the lower left, a +1 in the upper right. And since this time your scalar just ends up being 1 in the front, you don't have to distribute anything. We can write that our inverse of P would be the matrix 0, 1, -1, 1. And we have our 3 elements of the factorization that gives you A equals PCP inverse. So that concludes my video on section 5.5 in our brief introduction to complex eigenvalues and eigenvectors, and then a way that we can still factor 2x2 matrices if your lambda comes out to be complex. In the next video, we're going to move to our last section in chapter 5, and we're going to talk about an application of eigenvalues and eigenvectors for now. We're going to bring in another math class that's called differential equations, and I'm going to show you kind of how linear algebra and differential equations kind of cross over, and we can solve problems from that class using different techniques. If you're worried about you've never had a differential equations class, it's not a big deal. I'm going to teach you everything you need to know from scratch, at least for the problems we're going to do. And then whenever you go to a DE class, if you haven't gotten there yet, you'll learn different techniques and other strategies for solving these so-called differential equations.